And then the homework from chapter 1
This
and the
meeting is
Appendix A
being
slides
recorded.
on K-Maps is due next Wednesday, next week, not this Wednesday, right? Because we won't finish out Appendix A until Wednesday. So give you a bit of time to do the homework, ask questions next Monday, and get it all turned in. So any questions about anything we've covered up to this point? Or the course or anything at all. All right. So with the introduction, the basic takeaways from the introduction are sort of how computers are built, some of the principles of the computers, those 8 principles, and benchmarking for performance, right? So before diving into chapter 2 and the instructions or language of the computer, I thought it'd be useful to look at Appendix A and spend a little bit of time this week on what's underneath the instructions, right? So in chapter 1, we're building a computer out of silicone and other rare materials and chemicals, and it's an electrically based computer. And how is that organized in order to provide an instruction? Like for example, addition or a branch instruction or load and store instruction. So that's what we're going to do here in Appendix A. So the publisher doesn't have any slides for Appendix A. So one of my fellow instructors put together some slides and I've modified them a little bit. You can reach these off of Blackboard if you want to go back and review without having to run through the video. So what we'll do is sort of break it into 2 parts. And that's basically what we'll sort of see today's lecture and Wednesday's lecture. So we'll introduce the idea of Boolean algebra and why it's useful. And then this idea of our digital logic, our circuits, and what we can do with those circuits, right? And so that's what this discussion video is, and a little bit of background and a little bit of here's a useful technique that's used by people who are working through developing these systems. All right, this is everything I just said right there. So if we go back almost 2 centuries, George Boole published his treatise on the laws of thought back in 1847. And so what he was looking at, he was a mathematician, worked at Queen's College in Ireland. And I mean, here's a portrait of what he looks like, typical English man. And he was interested in various mathematical fields. And one of the other things he was interested in is having a more structured way to represent philosophical thought. Going back to Aristotle, right? And if you go there, then and you read Aristotle, you come up with these logical discussions and how you would organize and say things and ask things and reason about thoughts and other items. And so what he wanted to do was provide sort of a mathematical rigor or structure to discussions of math or logical thought. And so this is one of many things that he worked on. And so he developed this algebra, was binary logic. And And what he was looking at was to come up with a system of true, false, the ways to represent, the logical thought, and in and also operations that you could do as part of those, right? So I could have some sort of mathematical rigor to my discussions on the laws of thought. In a digital computer, we can equate true and false with on off, ones or zeros if we're just writing it down, or high or low voltage, right? When we're transmitting a voltage through the system. The original ENIAC actually wasn't binary, it was base 10, and it used fields and storage locations that had 10 values, right? 0 through 9, rather than binary logic, which was awkward and cumbersome in a hardware form to try and produce things. So Anostov and Shannon, and here's a picture of Shannon. So they're a century later. Boole published his work in 1847. Claude Shannon, in his early career, worked on encryption during World War II. And then after World War II, he was working at Bell Labs and looking at information theory and building digital circuits. And so in an analog or mechanical computer, you represent the operations, equations, and numbers using gears, right? And you have this assembly of gears, and you put in some input and you get an output based on these gear-driven equations. In a digital computer, we could do something a bit more flexible. And so what he realized is he could take this Boolean algebra and apply it to circuits. And so he called it switching, what was it called? Sort of like algebra. And anyways, he could apply it to the circuits that they were building in Bell Labs. And Bell Labs was a component of AT&T, and AT&T was building phone systems, and they got into also networks for connecting computers, and then of course also building their own computers. Plus, for example, the Unix operating system came out of Bell Labs. So it's been around for a bit. Now, just to refamiliarize ourselves with the basic concepts, true, false, and then we have operators that operate on those values. We have 3 basic operators, plus I'll list another 3 later on today. But we'll start with the 3 basic ones, and an or. And if both inputs are 1, the output's 1, otherwise the output's 0. Or as long as one of the inputs is 1, the output is 1. And only if it's 2 zeros do I get a 0. Typically, instead of using a symbol, we just simply place the variables side by side, and that tells us that we're doing an and of x and y. For or, if you're not going to write it out like and or, which you can do in some programming languages, we can use the plus operator with a Boolean variable or Boolean value, and that then signifies the Boolean or operator. And then negate, not x, simply flips the input for the output. There's a couple of different symbols for this. It's easier to find the little prime mark because I can just use a single exclamation point to represent that. There's an elbow symbol. This is supposed to be the overbar, but Google Drive decided to render it that way. But I have an image that shows the overbar later on in the slides. Okay, so there's our 3 basic operators. So then a Boolean function has at least one variable, at least one operator. So not X is a Boolean function. X and Y is a Boolean function. XOR Y is a Boolean function, because in that case, they each have two variables and an operator. And then we'll give it some input, right? So, and then the output of the function is also a member of the Boolean set. All right. So here we go. Just going to give you some random Boolean function, right? So X and not Z or Y. There is, in order to solve this Boolean function and see all of the possible outputs, what we'll do is build a truth table. And that's what we have right here. Now with 3 variables and 2 values per variable, that's 2 to the 3. And so that means I have 8 possible combinations, and therefore I have 8 rows, right? 2 variables would give me 4 rows. 4 variables would give me 16 rows. So I map out all the possible combinations, and then there's an order of precedence. Not has the highest priority, followed by and then or. So if I take a look, I'll do all the nots. There's one of them here. So I'll just have a temporary column, not Z, to solve for Z to not Z. And then I can solve for X and not Z. And now that I have those, for my third operator, I can take the results of X and not Z and OR it with Y and give us our final output. So for 5 of the inputs, there's an output of 1. And for 3 of the inputs, there's an output of 0. Any questions on how I got there? Or about Boolean logic or algebra at this point? All right. So what is this all good for? So what Shannon realized is that we could, our circuits are built out of transistors or, vacuum tubes. And so those are just switches. Switches have an on-off, right? Or at least these are binary switches. So they have a on-off, 1 or 0, true or false, high voltage, low voltage. And so circuits, we could build out of combinations of these switches, how we wired them together. And we could, instead of just looking at a mass of wires and switches on a board, I could write it out as a Boolean function and then, use my mathematical rigor to demonstrate that it had the properties I was interested in. And then I could also duplicate this and replicate this and use it over and over again, right? Now, in the course of developing our Boolean functions, the less operations or the simpler that we can make the function, the smaller the resulting circuit. So we always want to reduce our Boolean functions. What are we going to reduce them from? The standard form, and I'll talk more about the standard form later on today. But typically the way to do this is this reduction from the standard form down to our simple form is to use the Boolean identities. What I'll also show in the slides is an alternative way to do this. The first 4, identity law, null law, idempotent law, and inverse law. There's also one for the and one for the or, right? If I pick on like the first 2, 1 in X is always going to give me whatever the value of X is. 0 or X is always going to give me the value of X, therefore the identity. If I want to nullify it, 0 in X will always give me 0. 1 in X will always give me 1, right? And you can see there's slightly different forms for and or. These 3 should be familiar from prior algebra experience was regular algebra, commutative, associative, and distributive. The order of the operations, as long as the operations are all the same, doesn't matter, right? So whether the y is first or last, how I group the series of the same operations, and the idea that I can distribute from one form to another form, right? So what is that? 7, and then the last 3, absorption law. So here's obviously a good way to simplify things, right? And then basically a double negation or double complement. And then De Morgan's law is also quite useful, and I'll bring that up again because I've got a slide dedicated right to that. So here is all of the identities on a single slide, and also they're showing using the overbar symbol. So here is sometimes a different way people will show it, writing it out in a Word document or by hand. And we can see here the double complement. I'm not really sure how I would find 2 overbars in the font table, which I think is why this is an image that I grabbed off the internet and someone just drew all that horizontal lines for me. So what you would do is you would go through your non-simple function and try to apply these laws. And doing this takes time. It's a little tedious and it's a little error prone, and it's not really a focus of this course, but it's background that I just want you to be aware of. You can also see here, for example, we've done the associative law twice, the commutative law twice, the distributive law twice, the identity twice, and separated by other laws being applied, the null and the inverse. So we've reached out and touched a lot of these laws, 1, 2, 3, 4, 5, 6 different laws just to reduce this one expression. Now, the reduction is useful because down here, x and y, or not x and z, is 1, 2, 3, 4 gates versus or operators 1, 2, 3, 4, 5, 6. So you go, well, 4 operators versus 6. I only save 2, or a third. But think about if then this logic was inside of a loop, and I looped 1,000 times. Well, now I've saved 2,000 steps, right? Or I guess what I'm thinking physically, I'm not going to have this in a loop, but if I replicate this because I need this for, instead of a 1-bit operation, which is all this can do, if I want to use this for a 64-bit operation, then I would need to replicate this 64 times. And now I'm saving 128 operators. De Morgan's law is useful for doing the complement rather than the original function. So sometimes it's easier just to use, because I can always then negate the output by using a NOT gate, right? And so De Morgan's law allows us to do this, right? If we look, we can do x and y naught becomes x naught or y naught. And alternatively, we can go from the OR operator to the AND operator. And we can extend this quite far out. Useful background information. Now, the problem with the reduction or alternate forms is while they're logically equivalent, so if I go back here, one of the properties that has been maintained is if I fill in the same values for x, y, and z for the first function and the final function, I get the same output, right? A 1 or 0, whatever it might be. The problem is, for a human eye, me being able to tell you that this bottom function is logically equivalent to this top function, I just can't do that without sitting down and writing out the truth table for each of those. So instead, as I want to distribute my work, compare it with other work, show it off to people, what I do is rather than maintain it in one of these two reduced forms, I maintain it in a standard form, right? And so then the standard form I can compare to other equations or functions in a standard form too, and easily tell that no, these don't match, right? They don't look the same. They're not the same thing. They're not going to give me the same output for the same input, right? And again, just like with the identities, we have an and form and an or form. We sort of have that here with our standard forms. There's a sum of products. So we and the variables, and then we or the resulting min terms or terms. So I've got 3 terms here of 2 variables each. Alternatively, there's the product of sums. I will focus on the sum of products, but I'll talk a tiny bit about the product of sums just for completeness sake. And so in the product of sums, you look at the last word, sums. So we're summed the variables and anded the terms. 2 alternative ways of representing a Boolean expression. So if I have something and I know it's not in the standard form, because the standard form will actually have all the variables in each of the terms, which is not really shown in this example. So I may have to enhance or fix this example. In this case, this is that original expression I showed earlier. And we derived the truth table already from this one, right? So we had that from a few slides back. So what I would like to do is, given something not in the standard form, get it back to the standard form. That's easy and pretty mechanical. So I'll show you that. I'll do it for the sum of products and the product of sums, but I'll only ask for the sum of products. I must have like balloon expressions turned on or something like that. Oh, well, I'll figure that out later. But I'll only ask you to do the sum of products on the test and the homework. So, sum of products. I have the truth table for whatever function I'm planning to build the standard form for. And I look at the rows that end in a 1. So I can ignore the 0 rows. They're not going to work for me. And so in this case, I have 5 rows. For each row that ends in a 1, has a result of 1, I will combine the variables to build a term. And then I will OR that term together with the rest of the terms. So I have 5 terms. Each term will have 3 variables. If the variable has a value of 1, I just use the variable as is. If the variable has an input of 0, then I negate the variable. So I have not x, y, not z, or not x, y, z, or x, not y, not z, or x, y, not z, or x, y, z. So 5 terms, each with 3 variables, and I'm showing that right here. No longer in the simplest form, but it is in the standard form. So then I can compare it to other Boolean functions in the standard form much easier. Logically equivalent. So, which just makes sense since I derived this from the exact same truth table that I produced from this other function. So these two functions are logically equivalent, but to implement one of these functions physically, this is going to be much better. Because now, of course, in the standard form, I have 10, 11, 12, 13, 14, and an OR gates. And then I have 1, 2, 3, 4, 5 NOT gates. So almost 20 gates versus over here, I have 1, 2, 3 gates. So much, much better savings with the simple form. Any questions on how I derive the sum of products or the truth table? Those are both things I would like you to be able to learn from this chapter. Okay. Now, for completeness sake, I'll show you the product of sums, but I'm not going to ask you for this one on the homework test. So we'll see this one time in this one slide, and then it's there for reference purposes. This is the opposite. So it uses the 0 rows rather than the 1 rows. So instead of having 5 terms, it'll have 3. And the confusing part here is instead of saying not X, Y, Z, I will flip it, right? So this will become X or Y or Z and X or Y or not Z. So I flip the 1 and not X or Y or not Z. And you can see that over here. I've got my 3 terms. They're ANDed together, and each term has 3 variables. They're ORed together, and the variables are the negation of their original value, right? So if the original value was 0, then that's X here. If it was 1, then in this case for Z, that becomes not Z. Okay, so what is this all good for? What did Shannon realize? So Shannon and Anatov, what they realized is that we can represent our digital logic as Boolean functions. And furthermore, if I devise some sort of task, operation like addition, multiplication, division, any other operations that we'll explore in chapter 2, that I could represent those as some Boolean logic. And then when I implement it, I could translate that Boolean logic into a digital circuit. For the operators, we have gates. Now, our basic unit of operation that we had starting from the bottom is our electricity flowing through switches. The switches are either the vacuum tubes or, in this case, the transistors from the 60s onwards. Right? 40s to 60s, we had vacuum tubes. 60s onwards, we have transistors. And originally, we would assemble those transistors and manually wire them together on large logic boards. And eventually, we developed integrated circuits where we could all do this inside of a chip. And so I'll show a picture of that in a few slides. Now, symbology-wise, like if you're using a tool like Microsoft Visio or any of those drawing tools, if I want to represent in a non-textual, in a visual form, my logic, then I have these symbols. And or not. Little triangle is a circle, this curved shape, and this squared off shape. These represent our 2-input Boolean operations. or one input in the case of there. There are 3 other gates. I'd mentioned there were a few other gates earlier. And so we've got 3 more gates I'll mention. There's an exclusive OR. Basically, if the inputs are different, I get 1. If the inputs are the same, I get 0. And you can even find this little plus inside of a circle symbol somewhere in the font table if you want to write this out in a Word document or PowerPoint slide, right? See, highlights. So even Google Drive has that symbol represented. This up here is an image rather than the specific font symbol. And I think that's an image too. All right. And then the other 2 are very useful, basically because they save us money. There's a NAND gate and a NOR gate. 2 different ways to pictorial represent the NAND gate. One is AND negated. One is negate the inputs of an OR. And the reverse for a NOR gate, negate the output of an OR gate or negate the inputs of an AND gate. And that gets us the NAND and the NOR logic. And if you look, not AND is basically the reverse output of an AND gate, and not OR is the reverse output of a OR gate. So 6 gates, and or not, exclusive OR, NAND and NOR. So in an integrated circuit, how does this look? Well, you end up with something like this. You can still buy this 7400 chip. Originally, there was this big red and yellow volume paper, of course, before the internet. I mean, before the World Wide Web, 1974. And you'd flip through it and you could buy all of these. So what you saw is this progression, right? So starting out, you have individual transistors and you assemble them and you wire them together. That's very tedious. So the next step is I will do my transistor as a gate in a layer of silicone rather than having to build it from little bits and pieces. And I can then have many gates across this same surface, that wafer. And what I'll do is then wire them together, right? And so I'll do that by layering down layers of conductive and non-conductive material. So what I have here is a collection of transistors. There is 4 groupings of transistors here to build the 4 NAND gates. So the squares with a square inside of them are the inputs for each NAND gate, and each NAND gate has an output. And then, of course, regardless of the signal that I'm sending through it, I need to apply power. So I have power in and ground out. So 3 outputs are 3 wires per gate, gives us with 4 gates, 12 wires or pins. And then we need power and ground, so 14. So 7 pins to the side. So rather than laboriously wire out 4 NAND gates, I go buy this chip, the 7400N from Texas Instruments, produced in 1976, week 45, for quality assurance testing purposes. And then I can assemble larger amounts of circuits using chips like these, right? So this is what your computer in the 1970s would look like, is a collection of these chips in order to build a larger CPU or what other discrete logic that you would need inside of your computer. Right? The original Intel CPU was like, let's see if I can pull it up. Here we go. So the original CPU by Intel, that was a single chip, was this Intel 4004, a 4-bit processing unit. Um, says it would sell for about $450 nowadays with inflation, 60 bucks back in 1971. So that's a good chunk of change back in 1971. And you can see here, it has 8 pins on each side. This was insufficient on its own to have a CPU. So what you also needed was, there was an input and output chip that you needed. And there was then a memory chip that you needed. Can't remember the names. Right. Anyways, then you would put those chips together. Yeah, here we are. 4001, and I think one of these, the 4001, I can't remember. Anyways, one of these was the memory, and one of these was an input-output chip. And so you'd have sequence of these, and then there's a 4003. And so this is now my CPU, right? The actual brain part was a handful of instructions, is the 4004, but I needed to get data in and out, and I need to hold data, and that chip doesn't do that. So I need the other chips to produce that. And this is then, nowadays, if you look at the pictures like we had from chapter 1, where we had the ceramic for the A5 chip and several million transistors, this is, and then we have, these are resistors and capacitors and other components to connect all this together. The 4004 had 2,000 transistors inside of it. So that's basically where we're at, right? So we organize these in larger and larger patterns and go from, in that case, a few dozen transistors here to a few thousand transistors to 100,000 to a million to a billion to what we have nowadays in our modern CPUs. I mentioned the NOT and the NAND are useful because, or no, the NAND and the NOR are useful. They're known as universal gates. So they're straightforward and inexpensive to manufacture. And I can represent the other operations using combinations of NAND and NOR, right? So if I take, in this case, what I can do is just build one type of gate. I can build a NAND gate. That's it. So I have a NAND gate, and then if I put 2 NAND gates together, I have AND logic. If I tie one input into my NAND gate, I have a NOT logic. And if I use 3 NAND gates, I have an OR logic. So I can use the same manufacturing process, the same type of gate across multiple types of operations. So this speeds up development and manufacturing. I can also build different Boolean gates and have more than 2 inputs. I can have 3 inputs and 4 inputs. I can have multiple outputs. In this case, I'm going to give you Q or one result and the negation of that result and do it all in one logic chip and be able to provide that moving forward. Okay. Now, what I want to do is rather than us spend any time with identities, I thought just as something to take away from this course is if I'm actually developing logic circuits and everything, I'm not going to use the identities. There are some visual ways to do simplification of Boolean functions. There's K-maps, or Carnot maps. And there's also a tabular form. The tabular form is for when the number of inputs is above what a K-map can do. K-map is good for 2 to 4 inputs. Beyond that, you would use a tabular form. So I thought I could show you in just a handful of slides using K-maps. Again, another engineer at Bell Labs in the same time period, in the early 50s. And so he came up with this graphical way of building and simplifying Boolean expressions. So what we'll do is we'll take our standard function and map it into a matrix, which kind of looks like a truth table, but it's not quite. And then I can do grouping of the various cells in my matrix. And then I can build a term from those groups, combine it, and I now have a simple function. So here is our sum of products for a 2-input function, x and y, x or y. I have, with 4 inputs, 4 rows. These represent the rows that have a 1, right? Sum of products. So the missing terms, not x and not y, and also not x and y, will have the outputs of 0. So we've got 4 minterms possible. On 3 inputs, x, y, z, we will have 8 rows and 8 possible combinations. The minterms in this case are simply those terms from the standard sum of products form. And for the standard function that has those minterms, that would be the 1 output result, and otherwise it's a 0. Now this is a standard form, but it's also a very simple one. So this isn't really useful for our K-map example, but it's just to show how I build it. So here's our function. Here is our truth table. And then here is mapping our minterms into the matrix, right? So the matrix will have representation for each input. In this case, we have 2, x and y. So y will go across the top, x will go across the bottom or the side. And wherever the inputs are 1 and 1, we will place a 1 there. And there we go. Here is another simple form, simple function. If we map out the truth table, we end up actually having 3. Man, Google didn't like this. All right, let's clean this up a little bit. All right, good enough. Here is the standard form right there. Let me make it a little bit more easier to read. There we go. Nope. Undo that. All right. And so what might be easier to do the mapping to the K-map is to look at the standard form. I've got 3 terms and therefore 3 cells that have a value of 1. Now, this one was trivial. It basically is already reduced to its simplest form. Here, we've got the simplest form, and there's a reduction using identities on the left. And here is just a K-map or the truth table showing the simple form here, X or Y. But how do I get was a K-map from the standard form to X or Y? Well, what I do is once I build the K-map, I look for groupings, and I mentioned that earlier. Now, the groupings are horizontally and vertically. I don't do diagonally. So I can group this last column here, and I can group the bottom row, and they can overlap, and they can wrap, but there's no wrapping to be done here. By wrapping, I mean go around the edges. So this is the best way to show it, is just to give you a little picture. Uh-oh. Why is the picture not? There it is. Okay. For some reason, the picture wasn't showing up when I first scrolled over. All right. So now that I have this group, what I do is I see what the coverage of the group is. By coverage, I mean which values of the variable does it cover. If it covers both values of the variable, we can ignore that variable. Whatever the variable inputs, I don't care about it. In fact, we literally say we don't care. So if I look at the pink grouping, I don't care about Y, but I do care about X. And then for the green grouping, I don't care about X, but I do care about Y. So the pink one reduces to X. The green one reduces to Y. Those are our two min terms, X, Y. And now, balloons again, I OR them together, and I end up with X or Y. For the grouping, we only include ones. We don't do diagonals. We look at powers of 2, though a single one or a single value is fine. I look at that as like 2 to the 0 power. And then the groupings must be made as large as possible, and we can overwrap and wrap around the sides of the K-map. And I'll show you we got an example of overlapping here, and I'll show you examples of wrapping probably Thursday or Wednesday. So we have just enough time to run through a 3 variable, which is what I'll show in the homework, because it's a bit more complex, or it's complex enough to be interesting. To be honest, the 2 variable ones are normally super simple to solve, and so I won't worry about those. Now, notice a couple of key differences with 2 or 3 or I'll get to the other one later. With a third variable in a 2-dimensional space, I have to put that third variable somewhere. So I'll group it with here. So if I have Y and Z, then I have 4 possible combinations, 0, 0, 0, 1, 1, 0, 1, 1. Now, the other thing that Carnot found, Maurice, was that in order to do this easiest, what he followed was what's called a Gray encoding. Gray was an A as the name of a person. And what Gray looked at was in information theory, moving from one state to the other state was as little changes as possible. And so what we see here is to go from 0, 1 to 1, 1, I change 1 bit. To go from 1, 1 to 1, 0, I change 1 bit. If I had these swapped like I would traditionally, then to go from 0, 1 to 1, 0, I would change 2 bits. And then 1, 0 to 1, 1, I would change 1 bit. So make sure that you're cognizant of this, that there's a Gray encoding or organization for the columns here. So let's now use the K-map for 3 variables. So here's a standard form. It has 4 terms. The other 4 terms produce 0, so they're not included. If I map these 4 terms to my K-map, then I should have 4 cells as a 1 and 4 cells as a 0. So that's my self-check right there. And I have not X, not Y, Z, not X. All the not X's, these first 2 terms will be on the top row. These second 2 terms will be on the bottom row. Then I'm looking for not Y, Z, that's here. Y, Z, that's here. Not Y, Z, third location, and Y, Z, fourth location. Okay, now I need to group these. In this case, powers of 2. So I could have 2 groups of 2 each. You know, the bottom row and the top row are the left column and the right column. But I can build a larger grouping of 4, which is a power of 2. And I'm not doing any diagonals. I'm going up and down and left and right. And so now step 2, from my K-map, I build the groups. And therefore, I have one big group of 4. And then I apply the don't care rule. And I take a look. The big green blob ignores X. And it ignores Y. Because Y has a value of 0 and Y has a value of 1. And then for Z, I have the value of 1. So I do care about this because I don't have both values covered. And so this entire standard form function here becomes Z. You can build the truth table for Z, which is, 0, 1, and compare it to the truth table for the standard function, and you would find that they're identical. So these are logically equivalent. I didn't have to use any of those 10 identities. Boom. Much, much smoother and quicker way to do this. And I just want to illustrate K-maps as one of those neat things in our domain space that we would use if we were building our own logic systems. So I will stop here and I will pick up with more examples on slide 45 Wednesday. So have a good rest of the week until I see you on Wednesday.